Hi everyone, I'm Ye Tang. I'm a fourth-year PhD student in CPAS focusing on grid-tied PV inverters. Today I want to talk about the AC impedance derivation of utility-scale PV farm. Today we are seeing a higher and higher penetration of PV in the distributed system. There is concern that these PV generators will cause stability problem. To assess the stability of PV connection, the method used is called Generalized Nyquist Criterion, GNC for short. The advantage is that it doesn't need the dynamic models of the source or the load. We all know that how Nyquist criterion can be used in the DC system. In the AC system, after Park transformation, all the variables become DC values in steady state. So GNC can be developed for AC system based on AC impedance in DQ frame. The AC impedance here is a 2x2 matrix. The application of GNC works in this way that at PV connection point, PV impedance and grid impedance can be measured, and then the return ratio matrix LS can be calculated, and the two eigenvalues of LS can be plotted on Nyquist diagram. If the net encirclement of the point -1, 0 is not 0, then the system is unstable. The first step to apply GNC is to get the AC impedance of PV generator. I can derive the impedance using the dynamic model of PV generator. This model includes the dynamics of power stage, PLL effect, and all controllers. The derived results are validated by a scale-down experiment. The solid curves are impedances from derivation, and the star curves are impedances from measurement. They too match pretty well. Another conclusion from these results is that the impedance matrix is diagonal dominant if PV is under unity power factor or under Q constant control, but it is non-diagonal dominant if PV is under volt-var or Joule mode control. In this mode, Q is a Joule curve of AC voltage. The signs of ZDD and ZQQ are flipped compared to other modes. ZQD is comparatively bigger too. After getting the impedances of PV generator and grid, GNC can be applied to assess stability. In the first two cases, the connection is stable when PV is under unity power factor or Q constant control modes. But the connection is not stable if PV is under Joule mode. Joule mode control of PV may cause stability problems. The hardware experiment shown later will prove the assessment's results from GNC. This is the AC source. This is the line that represents the grid impedance. This is the PV inverter. And this is the impedance measurement unit that is connected between the line and the inverter. This is the PV emulator that is connected to the DC side of the PV inverter. This is the line-to-line voltage of the PV inverter. And this is the phase A current of the PV inverter when system is stable. When PV is under Joule mode control and the Joule slope is increased to a certain value to make the system unstable, this is how the system looks like. This is the AC line-to-line voltage, and this is the phase A current. Here's the end of my presentation today. Thank you for your attention.